And whenever you're ready.
Hello, everyone. My name is Jason Orr. I'm with Rhythm Engineering, and today I'm here to talk to you about NSYNC, Rhythm Engineering's adaptive traffic control system. And where the discussion really begins is at the local problems, the local level. The congestion, the start and stop traffic, the frustrated motorist. All of this is a product of inefficient driving. And these are some of the things that lead agencies like yours to contact Rhythm. This is also an example of a much more magnified global problem that inefficient travel has on fuel use and on safety and motorist happiness. Billions of billions of emissions are being pumped into the atmosphere every year due to unnecessary start and stop delays. The wasted fuel and the time stopped when we don't necessarily need to be. There's also a safety impact. There's nearly 30 to 40,000 deaths per year, and 40% of those take place at the intersection. Something I want to share with you here, the NTOC, which is the National Transportation Operations Coalition, they released a report card on the traffic timings in the United States, and it was given a D+. They found out that 70 to 90% of intersections are uncoordinated, unsynchronized. Most of them hadn't been touched in 5 to 10 years. And then we have here your local traffic signal engineer. As you can see, his office, it might be something familiar to you, but he's got too much work. He doesn't have enough resources, not enough money in the budget to handle a lot of these issues, not enough staff. He's getting phone calls similar to what you may get from frustrated motorists that are sitting at a light on the side street and calling and saying, listen, I have a red light. There's no one on the main streets. What's going on? And even though you may want to feel compelled to explain to that motorist, you just have to wait till it cycles back around, maybe give them a little bit of the technology. Honestly, they don't care. And you can understand that. They're short with you, they're upset, and they just want the light to turn green. And when we talk about these local problems and this frustrated motorist, we're speaking from experience. Our founder, our CEO, Reggie Chandra, the inventor of the NSYNC model, is a traffic signal engineer. He graduated back in 1993 from the University of Florida, and out of Springfield, Missouri, decided he was going to move to Kansas City to work with the Mid-America Regional Council on a project that was called Project Greenlight, and it was pretty much a timing operation program. So Reggie was intimately familiar with these traffic signal controllers. He understood timings, but he also knew the limitations of this technology. And even though through his best efforts, he was still reaching these limitations, he would still get these complaint calls. And so this is where NSYNC was born. It was born out of the idea from the inefficient traffic flow, that the inefficient throughput and the frustrated motorist has on pretty much our whole community. And this is where our mission comes from. It's very simple, it's very straightforward. Bringing loved ones to their destinations safer and faster. And notice it's not just faster, and it's not just throughput and getting down the road quicker. It's actually a big component, safety. And this is a key component in our mission as well as yours. And this is how we accomplish that mission, getting loved ones to their destination safer and faster, with the most widely deployed adaptive traffic control system in the United States. But before we talk about how NSYNC works and how the algorithms work, I want to talk a little bit about the impact that Rhythm has had with agencies like yours across the United States. All right, so that was a good example of a deployment with multiple challenges. This is the Jordan Creek Town Center here in West Des Moines, Iowa. And as you can see here, the red pins are the original deployment. You can see it's now expanded all the way up to I-80. There's also now a crossing arterial, Mills Civic Parkway. This is a considerable system, very large. It presents a lot of problems. There's a major retail space, the busy I-80 and their off-ramps, the seasonal time of day traffic. All this can then occasionally cause some saturation and backups. This area, this community is only a 70,000 population community, but during the day it swells to 130 people. And so the occasional saturation and backups happen often. You saw in that video some of the metrics that came out of that. There was a 24% reduction in delays. There was a 56% reduction in red light stops. That 7 intersection pilot program you can see there is now turned into over 85 deployments of the InSync system. That's now over 85%, over 75% of Jim Dickinson's and West Des Moines, Iowa's intersections in the entire community. running the InSync system. So sometimes we're asked, what about smaller deployments? Does InSync work well on a much smaller corridor? And so here's an example of that here in Upper Marion Township, just 2 intersections. This was PennDOT's first deployed system. The ADT averages between 70 and 80,000. And as you can see here, just north of the 202 highway there is the King of Prussia Mall. It's the busiest retail center in the United States. Considerable traffic on the 202, but variable traffic as well. Some of the before and after statistics, as you can see, was the time reduction that happened. 1 minute and 45 to get through just these 2 intersections. After InSync was deployed, only took 1 minute and 10 seconds. That equates to a 33% reduction in the travel delays. We also had a 20% reduction in stops. Pardon me, wrong way. We also, in regards to our stop reduction, there was a 20% reduction in stops, as you can see. Since then, Chad DeVitas, who is the traffic engineer for the Upper Marion Township, has continued to expand his system. The results have been so positive that the Pennsylvania DOT has now expanded to over 450 intersections throughout the state, and that's due just to this 2 intersection pilot program that we put in. So let's take a look at how we impact the environment, which can be important for funding mechanisms as well. If you're cutting down on those stop and start delays, if you're cutting down on the fuel used and the emissions going in the atmosphere, all these are products that are available for government funding. And so we're going to use this example here in San Ramon. It's a 5 intersection deployment here on Crow Canyon Road. It's just north of 680. And we were able to cut down on the fuel consumption daily of 114 gallons just on those 2 intersections, or excuse me, those 5 intersections. And if you were to calculate that out throughout the year on a 5-day work week, that would be almost 30,000 gallons of fuel annually. Here's another impact scenario and success story for us. In San Diego, the La Jolla Parkway. InSync is great on cutting down start and stop delays through an arterial. It's great for bidirectional progression, cutting down and better balancing the delay of a system. But what happens when we introduce InSync into a completely saturated system? The city of San Diego wanted to give us one of their toughest saturated areas to try to manage. And they found it here on La Jolla Parkway and Torrey Pines Road. It's just 3 intersections. And the reason there's so much saturation is due to the variability in traffic that can happen. And the reason is, as you can see here, the La Jolla Parkway and Torrey Pines Road, all of that leads to the beach. So you can imagine the variable traffic that can happen unexpectedly during the day and throughout the year and throughout the week. Some of our before and afters show that the delay and stop reduction improvements that happen on both the AM and the peak period. The AM peak eastbound, you can see, shaved almost 18 seconds off of the commute, which was a 48% reduction in time. For the stop reductions, we showed a 28% to a 44% reduction. And some of the other stats of the travel time and speed, we had an increase of up to 40% in the eastbound direction, nearly a 7 mile per hour increase. We also see that the travel time reduction that took place, on the westbound, 17 seconds, 13% reduction. And this was just traveling through a very small saturated network. So here's a good example of that. These are images of Google's Travel View. And the La Jolla Parkway, as you can see, would not only get backed up at the intersection, but it would get backed up almost all the way to the 5, almost a mile. You can see some of the before and after pictures. That red indicates a complete saturation where traffic is not moving. And you can see there on July 8th, in the AM peak, we had a queue that was almost a half a mile long. During that same time, a couple of weeks later with InSync, we almost completely eliminated that queue, that saturation. There again, we did it on Thursday, July 9th. You can see there the saturation, the backup, the queue that is developed. 2 weeks later, after the install of InSync, you can see there that we were able to keep vehicles moving and keep that saturation from happening. So one of our last examples of impact and statistics that we've had on agencies like yours and throughout the United States, North America, frankly, is VDOT did a very extensive study. It was a 5-year study. It was 151 intersections over 13 corridors. And here's some of the numbers that came from that. There was a 67% decrease in stops, 58% increase in average speed, 36% decrease in travel time. But what was the most telling of the metrics and what impacts us the most, and I would say everyone, is that 17% reduction in total crashes. And it wasn't just rear end crashes, it was angled collisions as well. So the system not only promotes throughput and getting their travelers to their destination safer and faster, but this also starts introducing an element that makes the driver start paying attention to the driving task. And this is critical for safety, that drivers pay attention to the driving task. And InSync has a tremendous impact on that safety. Also, the mainline travel benefit that you can see here, some of the ROI numbers that a lot of your constituents want to look at is you can see here that the mainline travel benefit was $43 million from this investment. And as you can see there, annualized out through a benefit cost ratio, it was nearly 9-1. So there's been a lot of studies on our system, not just the VDOT that I showed you there and not just some of our customers that have done before and afters. But if you go to our website, you can see here there are many different third-party consultancies and firms and organizations throughout the U.S. that have done studies on the InSync systems. There's a few I want to highlight: FDOT, VDOT, and PennDOT there at the top of your screen. Florida DOT, I'm not sure if you know, but they have a very rigorous testing, just like here in Texas, TxDOT, a very rigorous testing model before any type of traffic equipment is put out into the intersection and out in the field. VDOT, we've spoke about their system and that they just and their study that they just had. Also, PennDOT. PennDOT is now over 450 intersections in their state, and VDOT and PennDOT now is simply just speccing in InSync when a new construction project of a corridor or arterial is developed by the state. So these are some of our most predominant partners that use InSync, and they've done some incredible studies, and I think this is a great example of how organizations have done their due diligence to find the results before investing further. So you can see here the impact nationwide that InSync has had. We are now over 2,500 intersections and growing considerably year after year. On this map, you can see the installations. The green is for deployed systems. The orange is for scheduled systems to be deployed. The equipment's being installed and it's waiting for the adaptive system to be turned on. So how do we achieve this impact? So let's move into exactly how InSync works. You may have heard that InSync is a black box. It's a processor that you put in the cabinet. Nobody knows how it works. That could be not further from the truth. InSync system is actually a very straightforward in how the algorithms work and how it optimizes traffic flow and makes individuals get down the road safer and faster with better throughput. First, though, we have to take the intersection and go from an analog to a digital environment. And I'm going to show you how we do that. First, after we've done that analog to digital change in the intersection, we can then optimize locally through our local optimizer, and we can also then globally optimize through our global optimizer through a network of intersections. So you may recognize the picture on the left. It's a picture of an old electromechanical controller, probably from around the 1950s. You can see there it has a dial that spins in the middle, and the pins there will trigger relays. And those relays pretty much tell the light to turn red, amber, or green. It's a very simple, straightforward operation. It's pretty much like a sprinkler system timer. In fact, it is a sprinkler system timer. It's a very true cyclic analog operation. It's all predetermined cycle lengths. Now that device on the right, now that's a digital and solid state modern controller. It's the latest and greatest. You can program that controller with hundreds of timing plans, although you may not want to do that because you would then be in what our Reggie Chandra calls transition hell, going through all those time of day plans that your controller can actually accept. The point is that those controllers can hold a lot of timing plans. There's a lot of intelligence, digital solid state built into the controller. On the outside, it's touchy-feely touchscreen. But at the end of the day, that latest and greatest traffic controller is just emulating that analog controller on the left. That's why we call these electromechanical controller emulators. They work off of pre-programmed operations, pre-programmed cycles, predetermined sequences. And that little bit of intelligence that has recently been put into these modern controllers, it doesn't help you manage variable traffic any better than the one on the left. So here's a simple example of that we like to use to describe these analog operations. Think about an old television set and that dial that you used to have to turn. If you were on channel 5 and wanted to go to channel 10, you had to go through 6, 7, 8, 9, all the way to 10, through all those different desired states or phases to get to that desired state. If you want, so that's an analog architecture. That's what that old electromechanical controller was doing. And it's pretty much what the modern controllers are doing today. So what are we doing with NSYNC? Here's kind of another funny example here of how NSYNC works. Here's a picture from the 1920s, and if you can see there in the middle of the intersection, there's that tower, and in that tower is a police officer, a cop in a box, I think is how they used to refer to it. And he could actually, he was the traffic control. He was what controlled the red, yellow, and green lights, and he could actually see what was at the intersection and what was going on to control those signals. That was adaptive control. It was an intelligent, fully actuated system. It was dynamic, it was flexible, it was fluid, and it can make those changes happen immediately. He was not locked in, that control officer was not locked into any cyclic service of any kind. When we changed to those electromechanical controllers, we lost all of that intelligence. And that's essentially what NSYNC is. It's an artificial intelligence that sees what's happening in the intersection, and it can look down the line globally, and it can identify these platoons of vehicles to get them through the corridor. It was flexible, it was fluid, and it was dynamic, and it was immediate. And that's what we are replicating with the NSYNC system. So if you compare that to that old television set we talked about, NSYNC is actually the remote control. If you're on channel 2 today with that remote control and you want to go to channel 200, you just simply punch 200 and you're there. You instantly arrive at your desired state. That's what we are replicating with NSYNC. Rather than being locked into an analog, pre-timed, predetermined pattern, we've digitalized that intersection. And this is how we do it with the NSYNC processor. Showing two models here, the NEMA shelf mount version, and then the 19-inch rack mount for your 330 type cabinets. And how that processor works is, if we look here, we all recognize this slide here. We know that at a signalized intersection, there's typically 8 phases, 8 movements of traffic, the north and southbound left turns and through movements, followed by the east and westbound left and through movements. We also know that at that intersection, we know those phases to be 8 separate phases or states. They're non-conflicting, and those movements represent any 2 that can happen at one time. The genius about NSYNC and its algorithms is that we are not constrained to this locked sequence, this locked cycle that happens. NSYNC chooses its state to be in based on Q measurements, live Q and delay assessments. Here's an example. If we were to give each state a name, let's say NSYNC wants to call phase A up 1, A1 up. If after A1 it felt as though C5 could be served best, it can simply go straight to that. It's, again, not constrained by a single locked sequence. This is a true digital operation. And so how do we accomplish this? What are the 3 main components of the NSYNC system? Well, we use a video detection camera. It serves as the eyes of the intersection. And through these cameras, NSYNC is able to see what's happening at the intersection. And it can assess more than just vehicle presence. It can assess more than just if something's there or not. It can actually assess a queue by lane, and that information is directly put into the processor in the cabinet. That processor receives real-time information, second by second, and because of the ability of NSYNC to choose its desired state, it can make an immediate action, immediate decision, rather than something based on a cycle-based operation. NSYNC doesn't replace anything in your cabinet. It integrates with any type of controller in cabinet. And what NSYNC does is digitally chooses the state it needs to be in, serves that call to the controller for only those 2 phases to be served. Now let's talk about the local optimizer. NSYNC's cameras are able to do more than just simply view presence detection. During the installation, we not only set up our detection zones in those lanes, but we also draw occupancy segments going across, as you can see there. NSYNC constantly measures the volume of these occupancy segments and allows it to give it a queue, an actual queue of cars, and it can assess a delay. These percentage occupancy type and weight numbers help NSYNC to determine the best way to reduce those numbers, which state to go to next, which has the greatest demand in your intersection. It does this all while achieving great bidirectional progression through this global network of intersections. And there's a funny analogy that we like to use. It's the greedy algorithm and this greedy cop at the intersection. If you'll look up there in the top left corner of your screen, you can see that when a vehicle pulls up to an intersection, it receives a token. And for every 5 seconds that it's there, it receives another token. And it keeps giving them a token for every 5 seconds it's there for every vehicle that's in the intersection, for as long as they're in the intersection. But our traffic cop is a greedy cop, and he doesn't want to give out those tokens. He wants to get those tokens back. He wants to keep the vehicles moving. So what that greedy algorithm does is it turns to the state that has the most demand, that has the most tokens. That state gets the attention first. So in using that greedy algorithm, NSYNC can optimize at the local intersection based on real-time demand and delay. The second-by-second analysis of the intersection ensures that each phase is being served with a priority and not a predetermined cycle. If we see here at our phase sequence A1, we need 18 seconds, we can give it 18 seconds. If we find out as the cars move through, it needed less, we can then move on to the next phase. If we see that we need to extend that queue, then we can do that as well. But as you see, we don't have to move to A2 in our sequence next. We can simply say, if C2 would be best served, then that's what we can go to immediately next. So not only can InSync make mid-cycle changes, we're able to make mid-sequence changes as well. And if we put that together with the global optimizer InSync has built in, we have the most powerful adaptive system on the market today. So when looking at the global optimizer will schedule mainline progression, and our aim is to create these platoons of traffic moving through these green tunnels. All the other phases are then being served during the non-coordinated, unscheduled time. So in tying these concepts together, this digital operation that's going on in the intersection, the local optimizer and the global optimizer, we're going to use a calendar here for an example. And if you use Outlook, this may be familiar to you. I'm going to use 30-second increments of time, 10-second increments of time. And as you can see here on intersection 1, Monday morning, an AM peak, an adaptive configuration. And we may serve the westbound through for 30 seconds, followed by the eastbound through. Now notice they don't have to be scheduled at the same time because that may promote a better bi-directional progression. Now in the global optimizer, we repeat that pattern. Now we have our mainline movements already scheduled for a particular configuration, and we do that for the rest of the intersections in the corridor, intersection 2 and 3 for this example. Now the time between the start of one coordinated appointment, and when that coordinated appointment starts again, that's called our time between tunnels. So let's take a look at that white space here, this gray area that I have highlighted. That's the time that's unscheduled, those side streets, the uncoordinated through movements. This is where the local optimizer will go to work, doing what's best based on the real-time conditions that it sees. So let's say that during this unscheduled time, there's an influx in northbound traffic. InSync says to itself, I didn't have enough time to adequately serve all the movements in my northbound traffic. What it does is it simply calls down to the rest of the intersections in the global network and lets them know that we really need some more time to push this traffic through. So everyone in the network increases its time between the tunnels. And this allows for more unscheduled time to adequately serve all the movements. So when you shrink that calendar down and you connect the dots, it's upside down, but what you have is a time-space diagram. And where we don't have a global movement, where those black boxes are flashing highlight, that's where that local optimizer is going to work, serving the movements based on real-time conditions. So you can not only make mid-cycle changes, you can make mid-sequence changes as well. We often get asked about failures of mitigation failure, excuse me. InSync was designed with multiple layers. For example, if a motherboard goes out on one of our processors, it simply falls back to a controller operation by the dip switches that are on the front that allows those detector calls to go through onto the controller and let that controller go ahead and operate in an actuated state. If there's complete failure, we simply fall back to the controller operation. And remember, we're not replacing anything in that cabinet. If a camera goes down, the InSync processor functions as its own storage device. There's no central server that's reliant upon this data and upon the operation of the system. Each of those processors has a 30 days worth of stored information. If that communication goes down, going into the corridor, Well, the processors still continue to communicate. So your adaptive process is still happening. If the interconnect going into the corridor goes down, the adaptive process still works. You just don't have that ability to grow and shrink the tunnels if that interconnect between the intersection goes down. So having these failures, these multiple layers of failure mitigation are very important to a continued operation. And them not relying on a central server and not relying on communication going into the network for it to continue to work is what InSync is really designed to help mitigate some of that downtime and still have an adaptive system that's working. So how is InSync different from some of the other systems that are out there? There's a consultancy called Urban Systems Associates in California, and they wrote a paper on the different generations of adaptive. The first generation would be more of a manual-based system. It was developed in Los Angeles back in the mid-'80s. A second generation system is one that can take all that data and take all those numbers and try to do considerations for future cycles using that server and its algorithms. But the challenge with those systems is that it requires multiple amounts of detection to get all that data, just to get the best out of the system you have. So if we throw a few cars onto the intersection here, you can see them triggering detection points, single points of detection. Those could be loops, they could be radars, they could be video. And as you can see, they're placed at the stop bar in the advanced area and the upstream area. And all this might be needed to make a second generation even work properly. But even with all those deployed detectors, you're still missing a lot of the gray area, as you can see here. Cars can always be pouring on and off of mid-block, and that's passing, incorrect information down the corridor. So that's why we feel that the distributed architecture of InSync and what Urban Systems calls third generation adaptive, why it's so much superior. As we introduce these cars on the scene, InSync detectors are able to estimate the entire queue as far back as that camera can see. We really eliminate the significant amount of gray area you saw in the previous slide. We're able to see these cars as they come out of mid-block, and we're not passing on erroneous information down to the next intersection. This is what allows us to make these mid-cycle, mid-sequence changes. So let's compare this on a timing-based system, this responsive type systems of the second generation compared to the InSync real-time response that the third generation has. So if you see here, based on the time it takes to if you look at a responsive system and it sees in that responsive in a second generation system that it needs to make a change, that information is pushed to a server. The server then pumps out the new changes that need to be made, but that environment at that intersection is already moved down the road. Not the case with InSync. Through our though the mainline movements are pre-programmed and guaranteed within the system, you still have the ability to start and stop those movements early or late. And within that unscheduled time, we're simply serving those phases, those states between the coordinated movements at each intersection. You have the ability to extend those phases, extend the tunnels, truncate the tunnels. And every time you turn back to that local optimizer, the pattern may be completely different. Sequencing may be different. So all this time in our traffic industry, we've predicted these traffic patterns. With InSync, that's no longer needed. There's no predetermined cycles. no pre-programmed sequencing. Also, InSync has extensive software to help you control all of this. InTraffic is our central command console. You can access this software anywhere. It's not reliant on a server. You can use it from any device that it can access your organization's internet. We collect a ton of data, and we're able to push that data to you to help you better manage your system. You can look at different adaptive configurations. You can do what-if scenarios. You can adjust your green time and sequence and cycle lengths. You can also group your signals together. Maybe it facilitates a better flow through different corridors. And we do that through our intuitive drag and click configuration. And with our web UI, you can log in to look at your signals. You can see the real-time data and statistics that are going on. And all of this is collected and reported in a visualization program called Inform. Rhythm Engineering also has a very extensive service department to make these deployments more successful. We're available 24/7, 365. What happens is we come out during the installation to make sure that all the equipment is getting mounted properly and installed, whether it's your internal group or maybe the local contractor that's been hired. We run that data then for a couple weeks from the hardware. We then return to turn on the adaptive process. Our technicians return and help turn on that process with you. Glenn Bollinger, a traffic engineer out of Augusta, has said that this process and the way we do it is like having extra traffic signal engineers on staff. The InSync model, after we've left and the system is running, is like having extra traffic signal engineers on staff. We also include a 2-year warranty with our systems. Regarding the maintenance of our systems, you can spend as much time as you want. We have some agencies, they monitor it 24/7, and that's because they have a TMC and they're, a traffic management center that they're up and watching many different aspects of their environment. And so InSync is always up and running. They're always looking at it. But we also have some agencies, they don't log in for months. InSync was designed for that. It's designed for you to manage it as little or as extensive as you want to. And so our promise to you is after you get the InSync system installed, after we're able to turn on the adaptive system and have the opportunity to make the corridor run better, if after 3 months you're not satisfied, we'll issue a full refund on the equipment. So in closing, let's look at the things that burden us in the traffic signal industry, in the engineering community. The effects of transition. We talked about those controllers that can hold plenty of time of day plans, but what happens after you have multiple time of day plans in your system? Now you're just feeling the effects of transition all day. Those fixed cycles, the fixed sequences, the ring-based limitations that you're up against, and those time of day plans that just, with your best efforts, is not getting the throughput, the bi-directional progression you would want. All that limited by the modern day controller. And let's compare that and replace that with some of the real-time demand inputs and the real-time changes that InSync can provide. The immediate adaptation, the dynamic sequencing, the bi-directional progression that we talked about. These are all flexible changes that we can provide in demand. I'd like to thank you for attending this presentation. What I would like to talk about next is where InSync might work for you and some of the challenges you're facing that we discussed today. Thank you again.
All right, I'm going to go ahead and stop the recording.